Hi, everyone. Welcome to part 2 of lecture number 10. We have a little more theory to go over now about two-dimensional kinematics formulas, and then I'll cover 2 example problems taken out of tutorial number 10. So first, we're going to revisit our familiar kinematics definitions and formulas and equations from our one-dimensional problems, only we're going to rewrite them for vectors. So that way they will apply in 2 or 3 dimensions. Although in this course, we won't have any 3-dimensional problems. So although I may include a z component in these theory slides, for all of the example problems that we do, there will just be an x and a y component, and you can simply just omit all of these third components when you write down a vector for 2 dimensions like you see here from our textbook. So first of all, you might remember we defined all these quantities like position. The position of an object was just x or just y for our one-dimensional problems. Well, when an object is in 2 or 3 dimensions, it needs to have needs to have 2 or 3 position components all at the same time. So the object is located at some x comma y comma z in space, or just x comma y. We're going to combine all that into a position vector, which we call r. R is the position vector. Now, of course, the x or y or z position of an object can change over time. So that means this vector r can change over time as well. The vector r always points from the origin to the location in space where the object is positioned. So it's this vector here, that's the vector r. So if this is a little ball that's following some path through space, then the vector r will initially correspond to this vector here. And then as the ball moves along the path, then the vector r will be longer and point over to whatever the new position of the ball is at any future time. The velocity of an object before in one dimension, we omitted this subscript because it was understood that that was the velocity in the x direction, or for vertical problems in the y direction. But now when an object moves through 2 or 3 dimensions at the same time, it can have x and y components and z components of the velocity. So we can have all 3 of those components simultaneously. So vector v is now the instantaneous velocity vector. All of these components can change over time, so this vector v can then be different over time. It works out really nicely that the tangent to this path through space that the object is going to travel, the direction of that tangent is always going to be the same as the direction of the instantaneous velocity vector. Okay, so if the object's path through space is like this, then the instantaneous velocity right here at the top of the path is exactly to the right. The instantaneous velocity right here is to the upper right. Okay, so keep that in mind as we think about our projectile motion problems coming in lecture 11, and we draw the sort of parabolic path of an object of a projectile as it travels under gravity. Then the instantaneous velocity at any moment in time is going to be tangent to that parabola. Now, acceleration, again, an object could have acceleration in more than one component at a time. In our free fall problems, all we're going to have is idealized free fall problems with no air resistance. All we're going to have is a y component of acceleration in the negative y direction. And there won't be any other, there'll be 0 for the x or z components. However, in real life, if there's air drag or a thruster on the object or anything else, that creates additional components of acceleration as well. Now, one quick note about notation. As you know, when you have a vector v or a or any other vector, it's traditional for when you want to refer just to the x component to write the name of the vector without bold or without the hat. Just write the letter of the vector, and you'll see in print it's italicized, and then you add the subscript. Okay, so you take off the boldface or take off the hat. However, there's an exception. For the position vector, we don't usually write r sub x, r sub y, r sub z for the components. Why? Because the x component of position simply is x. It is a Cartesian coordinate x. The y component of position is simply the y position, y, and so on. And the second thing is instantaneous speed. You may remember for one-dimensional problems, it was equal to the magnitude or absolute value of the velocity. That is still true, even if the velocity is 2 or 3-dimensional. The instantaneous speed at any moment in time t is equal to the magnitude of the velocity vector. Again, it's traditional to write the magnitude of velocity to write the magnitude of any vector either with these double bars on the sides, sometimes single bars, or just rewrite the vector name without the boldface or without the hat. So what that means is when you see this now, we're talking about the magnitude of the velocity v at some time t. That is synonymous with speed instantaneously. Now, let's review 3 of our equations from kinematics, only we're going to rewrite them and recast them with vector notation instead. So you may remember that that displacement was defined as final position minus initial position, or sometimes we wrote the final position as just position, right, x at time t, or minus x at time 0, x naught. So in other words, it looked like this. Okay. But what if we have y and z positions all doing the same thing at the same time? So we have a final x minus initial x, final y minus initial y, final z minus initial z. So the compact way to write that would be final position vector minus initial position vector. And if we expand that and do the little subtractions, what we find is, what do you know? The first component of this becomes just delta x. The next component is delta y. The third component is delta z. So the compact way to write this is just delta r. So delta r, like every other quantity we've had with the delta r is just final r minus initial r. And when you expand it all out and write out all the notation, what you find is that the components of the delta r vector are delta x, delta y, and delta z, which are the displacements. These are our familiar displacements, right? Just horizontal displacement, vertical displacement, and out of the page displacement. Do you remember our definition for average velocity? It was equal to displacement divided by time, right? So that's exactly what we have here. Displacement, delta r, is still in the numerator. Only when we divide by time, time is not a vector quantity, it's a scalar quantity. So notice that this is just a scalar multiplication. We're taking the displacement vector and we're multiplying it by the scalar 1 over time. So this will have units of 1 over seconds. And so what you want to do is, if once you know the displacement vector, you just multiply it through by 1 over the elapsed time, and that gives you the average velocity vector. So notice how the average velocity, time is always positive, so this is always going to be a positive scalar. So that means the average velocity vector will always point in the same direction as the displacement vector, just like this diagram right down here. So notice if the displacement vector between time 1 and time 2 looks like that, okay? Now notice that's R2, the position at position 2, minus R1, the position at position 1. So that gives us delta R right there. Notice the average velocity of this object over that time interval from T2 to T1 is going to point in the same direction. It'll have the same direction as the displacement vector. Similarly, if we look over here, remember our definition of average acceleration? It was equal to change in velocity over time. Change in velocity now is going to be v2 minus v1, or v final minus v initial. And as you can see, that's a subtraction of 2 vectors. Okay, so if this is v2 at some later time 2, and this is v1 at some initial time 1, if we draw v2 minus v1, then we wind up with a delta v that points in this odd direction. Look at this. It points. It turns out it will always point toward the concave side of any curving path. Okay, so that'll be the direction of the acceleration of the delta v. Pardon me, of the delta v. And what we can see here is, again, because time is always a positive scalar, the direction of the average acceleration over that time interval will always point in the same direction as the delta v, which again will be in the direction of the concavity of the path. It just coincidentally turns out to be that way. This will come back when we talk about circular motion, when the direction of the acceleration during circular motion is always toward the center of the circle. Okay, so that's sort of once we learn circular motion, that'll be an easy way to remember this. Okay, so once again, this is just scalar multiplication. The vector part is over here. Finding v final minus v initial, or v2 minus v1, that's going to be the laborious part with the vector math. But then you just multiply through by 1 over time, which is a scalar, and you wind up with the average acceleration vector over that time interval. And notice how the average acceleration vector points in the same direction as the delta v vector. Now, quick little quiz. Do you remember what the formula was for average speed? Okay, what was the definition of average speed? It was what quantity over what quantity? Okay, I hope that you remember that it was equal to path length or position or distance traveled, total distance traveled divided by time. Now, total distance traveled, remember, is the length along the path that the object takes. So it would be the length of this curve, this blue curve here, right? Or the length of the dashed blue curve there. There is no one formula for that, right? We have to figure it out custom for every problem. And it has no sense of direction, right? We're adding up distances, we're adding up this sort of length that is curving through space. So there's no one sense of direction to distance traveled. The same thing is true of time. Time's also a scalar. So therefore, speed has no direction. Speed is a scalar. It is total distance traveled divided by time, meters divided by seconds. Same definition as we had before for one-dimensional kinematics. So this definition is unchanged. There are no vectors in this expression. They're all positive values. So therefore, the speed is positive as well. Okay, so this is average speed, not instantaneous speed, which we had on the previous slide. All right, that's it. That's all of our theory, reviewing our equations of kinematics that we learned before for definition of displacement, average velocity, average acceleration, average speed. And now we're going to apply these to some two-dimensional problems. So again, we won't do any three-dimensional examples. I'm going to show you a solution for problem 4 and problem 7. So these are a little bit long. So, and then that's it. That'll be the end of this recorded lecture video. So these are a little bit long. So if you prefer, instead of watching the video, you can simply look at the written solutions that I've already posted for these tutorials. Um, and you can practice the similar problems, which are numbers 3, 5, 6, and 8 that use a lot of the same formulas that we've just covered on this slide here. Okay, so we'll put most of these formulas to use now on example 4 and example 7. So I'm going to switch to, instead of using my stylus, I'm going to switch to doing this on pen and paper. Okay, all right, so here's problem 4. So suppose that we have a little rover on the surface of Mars. It initially travels 30 meters due north, then it pauses, turns, and travels 15 meters due northeast before it stops. Okay, so we don't know, at this moment, we don't know how long it takes to travel north, how long it pauses, or how long it takes to travel northeast, but we do know the directions and the lengths of these displacement vectors. So there's two displacement vectors that are described here, 30 meters due north, 15 meters due northeast. And then part A asks to find the total displacement of the rover from its starting point. Just looking ahead, what will the rest of the problem ask for? Part B will ask, what is the average velocity over the entire trip? So remember, the formula for average velocity that we just saw requires the total displacement, and then we'll divide by time or multiply by 1 over time. And then what was the rover's average speed over the entire trip? Okay. So first, let's solve for average, let's solve for the total displacement. All right, I'm going to zoom out one bit here because these vectors are going to be a little big. So first, let me do a graphical representation of this vector sum. Okay. So if I decide, let's call this, these are two displacements. Let's call 30 meters due north. Let's just call that D1. You're welcome to name it something different if you like. And then, but I'll just follow the nomenclature I chose for my solutions. And we'll call that second displacement D2. Let's see what the displacement sort of look like if I were to sketch them in a semi-accurate manner. Okay, so the first displacement is due north. So I want that to, I think I need to start a little lower on the page because otherwise I'm going to run out of room. Okay, so I want that to look like 30 meters long due north. So that we'll call that D1. And then the second displacement will be 15 meters long due northeast. So I'll make that one half as long, and I want it to point due northeast. Okay. And let me label these briefly with their lengths. So this one is 15 meters. I'm sorry, I'm dropping the 0.0 sig fig just for simplicity on my diagram here, but we'll remember we'll remember the number of sig figs for our actual calculation. All right, and then that's it. So the sum of those two vectors is the vector that goes from the start of the first vector to the end of the last vector as the crow flies. So I'm going to draw this vector sum. This is the net displacement, also known as the total displacement. Right? Let's call that d total. Okay, so here I have my graphical representation of the vector sum. All right, so now I have a choice of how do I want to then perform this vector addition, right? So here's my vector addition written out mathematically. It looks like that. I have a choice of doing it either via the component method or via the triangle method. So the triangle method works best when you have usually just two vectors, or maybe three if they sum to 0. And if they form a nice symmetrical triangle, then we can use our geometry and trig to solve for any other lengths of the triangle or angles within the triangle that we don't already know. This triangle is not quite as nice and symmetrical as we'd like. When you have a scalene sort of, an odd triangle like this one, then you can still use the triangle method, but you would end up having to use law of sines and law of cosines to solve for any unknown lengths or angles like we want here, okay? So what I think we'll do instead, and what do we ultimately want? We want to get the magnitude and direction of the total displacement. So here's the magnitude will be the length of this vector here, and the direction, right? Assuming this is the positive x direction here, the direction will be that angle there. So we know D1 is due north. We know that that one points at 90 degrees. So one way to get at that would be to get this angle, this little angle here in the middle of the triangle, if we did the triangle method. So if we did the triangle method, we want to find that the length of that side and this unknown angle. However, I think this might be a good example for us to demonstrate the component method. Okay, so for the component method of vector addition, what we want to do is we want to express d1 and d2 in components, calculate those components if we don't already know them, if we're not given what they are, then use the components to perform the addition, and then when we're all done, convert those the added components into magnitude and direction to get the final magnitude and direction that we want. So I'd say it's both of them are probably close to the same amount of work in this case, but I'll just go ahead and demonstrate the component method. So I'm going to write D1 in components and D2 in components, so that way I can add them together and find D2. Okay. So D1, it looks like I can simply write that one in components just by inspection. Okay. Knowing that my directions, positive x, if I define positive x to the east and positive y to the north, then I can see that D1, which is due north, lies exactly along just the y-axis. So it has no x component and only a y component. So so we can do this one by inspection. Okay. What will the x component of D1 be? Just by inspection. It looks like it has no x component at all. And what will the y component of D1 be? Just by inspection. Looks like it'll be 30 meters. So we got that one by inspection. By inspection just means it's simple enough that you can do it just by looking at it. And then for D2, all right, for D2, let's consider what's the trig angle of D2. We know the magnitude of D2. The trig angle in this case, we're told that D2 is due northeast. So I can just tell by inspection that's 45 degrees. Okay. And in that case, let's apply our traditional formulas now for figuring out the x component of D2. So here, let me be really explicit. I'll write it all out. We know that the x component of any vector is equal to the magnitude of that vector times cosine of the trig angle of that vector. We know the y component of any vector is equal to the magnitude times the sine of the trig angle of that vector. So in this case, that's going to be equal to 15 meters times cosine of 45 degrees, comma, 15 meters times sine of 45 degrees. Okay, so that's my x and my y components. And I ask my calculator what those are, and it turns out they're both the same value because that's what happens with 45 degrees. Okay, so that's D2. Great. So now, if I want to find out what D total is, I just do a big addition problem here, right? I'm going to add the x components of D1 and D2 together, and that'll give me the x component of D total. And the y components of D1 and D2, I'll add those together, and that'll give me the y component of D total, right? So this will be x component of D total and y component of D total. So I add up those x components, and I just get 10.61. And I add up the y components, and I get 40.61. Great. So we're 2/3 done now with the vector addition, right? Well, actually, let me correct that. The vector addition part is now done. We've now added vector D1 and D2 together, but we know the answer in components, and we're asked for the answer in magnitude and direction. So now how do I convert components into magnitude and direction? So that'll be the final step. So to get the magnitude of any vector when we know the components, notice how when we write the magnitude, we take off the vector hat or the boldface. I do this Pythagorean looking sum or quadrature sum of the x and the y components. So that'll be equal to, okay, just copying over from there. And I ask my calculator what that is. My calculator says it's about 41.97. And now at this point, that's when I say, okay, you had 3 sig figs for all the values. Unless there was some big carryover or cancellation or something, it's probably 3 sig figs for the answer. And then direction. We have a nice sort of cookbook formula. If we know the x and the y components of a vector, then we can get the direction of that, the trig direction of the vector, right? By taking the y component over the x component. Inverse tangent, y component over x component. Notice that the units will cancel, which is what we want, right? So that way we're feeding the inverse trig function a dimensionless quantity. And then I ask my calculator what that is. My calculator says 75.4 degrees, and I know that there's another answer that's 180 degrees away from that, because inverse tangent is 2 answers on the unit circle. So that I add, if I need to at least check out that other answer, right? Now, which of these is correct? How can I tell? Okay, for the trig direction of the total displacement of the rover. Well, there's a couple of ways. One is, and this is the most sort of the most robust way to do it. What if I don't have a sketch? If all I know are two components, and I look at the minus sinus on these two components, and I see that the x component is positive, the y component is positive. Which quadrant has positive x and positive y? The first quadrant. So I know that that is the quadrant that I want. This other one is in the third quadrant, so I discard. Okay. Now, the other way to do it is if we have a sketch, and we know, oh, I know the total displacement is up here in the first quadrant. So then I can also just tell by inspection that I want the first quadrant answer and not the third quadrant answer. So I didn't even need to calculate that one. If I figured that out, if I identified this as first quadrant, figured that out, then done. Good. All right, so now we can say, all in all, the total or displacement is 42 point. Now remember, this is a total vector, so magnitude and direction at 75.4 degrees trig direction. But notice all the answer choices here are not given in trig directions. They're given in degrees east of north. So looking at my sketch up here, here's my trig direction right here. What are the degrees east of north if I look at my axes? So to the east of north means starting at north, how many degrees to the east do you go from north? So it's this angle right here. I might call that alpha. Okay. How do I get alpha knowing theta? Well, it looks like the two of them are going to add up to 90 degrees, right? So they're the complements of each other. So I'm going to say, okay, alpha, the degrees east of north, is equal to 90 minus theta. So that's going to be 42.0 meters at 14.6 degrees east of north. Okay. This isn't the same exact thing as compass bearing, right? Compass bearing would be, well, actually, in this case, in this particular case, it actually is. Compass bearing is anywhere in the 360, starting at north, going through east. So going around as far as you need to. It turns out, in this case, that's actually the same. So that's it. So let's keep this in mind. We now know d total in magnitude and direction, and we know d total in components. So we can use either of those in the parts of the problem that are coming ahead. Okay. So the next part of the problem, part B, asks what is the average velocity of the rover over the entire trip? And then part C will ask us about the average speed. Okay. So let's set part C aside for now and just look at part B. So part B, average velocity is defined as displacement times, divided by time. But I want to write it this way because it reminds us that this is a scalar multiplication, right? So 1 over the total elapsed time is going to be the scalar that we're multiplying our displacement vector by, right? So this is the displacement vector. And this will be the net displacement over the entire trip, right? That's what this problem is asking about for the entire trip. So let's just first do a quick calculation here. All of the answer choices are in centimeters per second, and we're given the time in 18 minutes. So how do I go from minutes to seconds? Let's do a quick unit conversion. So I multiply by 60 seconds, and I get 1,080 seconds. All right. So now we can do our vector multiplication. So this is 1 over 1,080 seconds. That's a scalar. And we're just going to multiply our vector, which is 42.0 meters at 14.6 degrees east of north. Now I can just leave my direction like this, okay? I don't, because notice how all of the answers are also in east of north. So I don't need to convert it to trig direction just to convert it back. I'll just leave it this way for now. Now, when we multiply a vector by a scalar, first of all, how do we get the new magnitude? Okay, the answer you may recall from our previous lecture on vector arithmetic. When you multiply through by a scalar, the new magnitude of the final result is going to be equal to the absolute value of the scalar you're multiplying through times the magnitude of the original vector, okay? And the magnitude of the original vector is always positive. Okay, so we just got to make sure that there's no minus sign. We don't want to wind up with a negative magnitude when we're done. Right? And then what happens to the direction? Well, there was only two choices. If the scalar you're multiplying through by is positive, then the direction does not change. And that's true in this case. Time and 1 over time are positive quantities. If the scalar we're multiplying through by was negative, then we would simply flip this direction by 180 degrees. You could add or subtract 180. It doesn't matter. Either way, you've reversed the direction. But in this case, we don't have to do that. So I asked my calculator, what's 1 over 1080 times 42? And the answer I get is 0.03886 meters per second. Okay, and the direction doesn't change. All my answer choices are in centimeters, and plus it's a 3 sig fig problem. So I'm just going to round this to, I'll quickly convert to centimeters by moving the decimal place 2 to the right. So it's 3.89 centimeters per second. And the direction is unchanged. Great. Now, for average speed, What was our formula for that? Now, this isn't instantaneous speed, right? This is average speed. So I think I'll stick to using the S for now, right? Although, like I said, most of the time, you won't see S used for speed. Going forward, you'll usually see S used for things like path length. That was equal to total distance traveled divided by time elapsed. Well, we know the time elapsed now from up above. We know the 18 minutes is 1080 seconds. What about total distance traveled? The total distance traveled is the magnitude of vector d1 plus the magnitude, then there was a pause for the rover, and then there was the magnitude of vector d2, and then the trip was done. Right? By the way, this is a long way to write magnitude, or you can just write it as just plain d1, just plain d2, without the vector hats and without the double bars. I'm just being extra explicit here. So that's equal to 30 meters plus 15 meters. So the total path traveled, traced out by the rover, if we look back at our original sort of vector diagram here, the total path traced out by the rover was 30 meters plus 15 meters. Notice how we've now lost the sense of direction, right? We're mixing directions when we ask what's the total path length traced out by the rover, okay? So this 45 meters here does not have a direction attached to it. So now I can calculate the average speed. 45 meters divided by 1080 seconds. And my calculator says the answer is 0.04166 meters per second. Let's convert that to centimeters and also round off to 3 sig figs. So 4.17 centimeters per second. All the answer choices are in centimeters per second. Okay, great. So that's all of problem number 4 with the Mars rover. Let's switch now to problem number 7. And that'll give us an example of using the average acceleration formula. It'll also give us a chance to practice some more vector addition as well. So problem number 7, suppose that you have a race car being test driven on a flat desert plain. It starts with an initial velocity of 30 meters per second at 90-degree trig angles. So for this problem, I decided to stick with just trig angles and not give you compass directions. Okay, so that'll be, let's call that initial velocity. We can call that v initial or v1. I'll call it v initial. I don't think there's going to be more than 2 here. And then the car drives around. So initially, it's driving at a trig angle of positive 90 degrees at a speed of 30 meters per second. And then after driving around for a while, it winds up at some later time, 12 seconds later, with a final velocity of 75 meters per second at 180 degrees. So let's call that v final. Okay. What are the magnitude and direction of the average acceleration during this time interval? And here's the time interval, 12 seconds. All right. Well, let me visualize a little bit first what these vectors look like. Okay. So v initial is 30 meters per second, sort of at a trig angle of 90 degrees. If you wanted to call that a compass direction, that would be sort of north. But let's just stick with trig angle. So here's v initial. And the magnitude of this is 30 meters per second. And then at some later time, the final velocity is considerably larger, right? It's more than twice as big. And it has a direction of 180 trig angle. And its magnitude here is 75 meters per second. So what's our formula for average acceleration? Average acceleration vector was equal to 1 over time times the delta v, right, which is v final vector minus v initial vector. So this is a vector quantity. We're multiplying by 1 over scalar, and we'll get a new vector quantity then when we're done. So let me just be a little explicit here and write this out. And again, this is a scalar multiplication here. This is the vector math part right here. Oops, that's supposed to be a minus v initial Okay. Now, just to help me with visualization a little bit, I'm going to draw a little graphical sketch over here of what this vector subtraction should look like. Okay. So I have v final minus v initial. So here's v final plus the negative of v initial. So v initial points upward at positive 90. So here's the negative of v initial. So v final plus the negative of v initial means that delta v should look something like this. Now, why am I bothering to check out the direction of delta v? Okay. So delta v is v final minus v initial. So it's v final plus negative v initial. So why am I bothering to do that? Because I can see that the direction of average velocity vector should be the same. This is a scalar, positive scalar. It should be the same as the direction of the delta v vector. So now I've just figured out, this is also going to be the direction of my average acceleration vector. So my average acceleration vector should also point in exactly that direction. So I know now it's in the third quadrant. Good. That's something for me to just pay attention to, so to sanity check at the end to make sure that everything works out. All right, so now at this point, I need to decide how am I going to do this vector addition right here. I mean, technically it's a subtraction, but addition is the same thing. Okay. I can either use the triangle method, which it turns out in this case would be nice and simple, right? So this is a nice right triangle right here. I know the lengths of the two legs of the right triangle, and what I want to find would basically be this direction and the length of this hypotenuse. So the triangle method would be great. Okay. And what am I asked to find at the end? Am I asked to find components? No, I'm actually asked to find magnitude and direction. So that would work out really well. The other option would be the component method. That would be to write out v final and v initial in components, add up the components together, and then convert the final difference of those vectors, right? The subtracted delta v, convert that. Convert the A average, multiply through by the scalar multiplication, and then convert that final thing into magnitude and direction at the end to get the magnitude and direction that we want. So I have a choice. I can go either way. Triangle method for the vector addition part, vector subtraction part, or component method for the vector subtraction part. And then at the end, I still have to do this scalar multiplication and then make sure my final answer is in magnitude and direction. Let's use the triangle method. Okay. Okay, so for the vector subtraction part, let's use the triangle method. So what I'm going to do is I'm going to turn this into this primitive geometric figure where I remove the little vector arrowheads from the vectors, and I write down the lengths and angles, all the lengths and angles that I know for this triangle. So this is a length of 75 meters per second on that side. I know this is 90 and 180 degrees, so these two are at 90 degrees to each other. And then V initial was 30 meters per second on this side. What do I want to find? I want to find the length of this side, which is delta V, and I'll ultimately want the direction of delta V as well. So what I'm interested in is this angle, which I'll call alpha over here in this corner. All right, so let's find out what those are. Okay, so first of all, the magnitude. I can see Pythagorean theorem will work pretty well. Delta V is equal to the square root of V initial squared plus V final squared. I ask my calculator what that is, and I get 80.78. Let's keep some extra sig figs for now to prevent round off errors. Okay, so even though this is looking like a 2 sig fig problem, do not round to 2 sig figs for intermediate values. Carry 1 to 2 extra significant figures. Or if you have a value on your calculator screen, you can just leave it all there. Okay. So that's the magnitude of delta V. So just to be clear, this is the magnitude of the vector, right? And then direction. At this point, I know all three sides. So I could use inverse sine or inverse cosine or inverse tangent. I think I'll just choose inverse tangent. Tangent of alpha was equal to opposite over adjacent. So therefore, alpha is inverse tangent of opposite over adjacent. Okay, notice the units again are going to cancel. Great, that's what we want. And ask my calculator, okay, what's the inverse tangent of 30 over 75? My calculator tells me the answer is either 21.8, which is what it tells me on the calculator screen. And then I know that there's another answer that's 180 degrees away, which is 201.8. But if I just look at my drawing here, this triangle drawing, alpha is clearly an acute angle. So therefore, I know that this is the value for alpha, okay? But I'm not quite done because that's not the trig direction. And notice how all of our answers are looking for trig angles. So looking down the road, I know I'm going to need the trig angle for the average acceleration, which means I want the trig angle for delta v as well. So how will I get the trig angle of this delta v vector right here? Well, if I put it at the origin, what I can see is that the trig angle is all the way around from the positive x direction to the vector. So it looks like I want to take the little angle alpha and add 180 degrees to it. So what that means is that for the trig angle, or trig direction, it's equal to 180 degrees plus alpha. What do you know? I'm just going to get this, I'm going to get that same value again. So that's the trig direction, right? All right, good. So let's summarize that. So therefore, in summary, the vector delta v is equal to 80 point, I'm not going to round off I'm not done with the problem yet, so I'm not going to round off sig figs yet. 80.78 meters per second at a trig direction of 201.8 degrees. Okay, so now finally, we still have one more step left to do, right? So that's my vector addition or subtraction, all done now via the triangle method. The last step is still to do this scalar multiplication, right? So now I want to take my delta v vector that I just found and multiply by 1 over time. Okay. And the time is given in the problem as 12 seconds. So now we'll do the final. So now we're going back to our original equation again, the definition of average acceleration. And I'm going to multiply my vector delta v here by 1 over 12 seconds. Okay, now again, scalar multiplication by a positive scalar. The answer is going to be the absolute value of the scalar. So it's absolute value of 1 over 12 seconds times the magnitude of the original delta v vector. And then, so I can calculate that, and the answer I get is 6.731 meters per second divided by seconds. And then what do I do with the direction? I look at the sign of the scalar I'm multiplying by, and if it's a positive scalar, then I leave the direction alone. And if it's a negative scalar, then I flip the direction by adding or subtracting 180. Well, it's 1 over time. It's a positive scalar. I leave it alone. Now, at this point, I can round sig figs. And sig figs are weird on angles. I'm just going to look at the answer choices. It looks like they're all rounded to the nearest degree. Now, let's finally, let's reflect and sanity check on our final answer. Looking back at my original, so 6.7 meters per second squared, does that seem sort of reasonable? Yeah, it looks like over 12 seconds, if I were to keep changing this, the initial velocity by about 5-6 meters per second every second for 12 seconds, yeah, that would probably be what I'd need to do, okay, to get up to 75, something like that. But the important thing is also the direction. If I look at the direction of delta v over here, and I remember how at the beginning I said that's also going to be the direction of the acceleration. 202 degrees. Does that look right? Yes, it's in the third quadrant, just a little bit down from 180. Perfect. So that's what I expect. Good. Okay, that's the end of lecture number 10. At this point, I suggest that you either try the additional remaining problems on the tutorial sheet as much as you'd like, but of course those are just for practice. So whenever you're ready, go to the online homework and do the online homework number 10. That is for credit.